The last sort we learned about was the very powerful idea of Radix sort, allowing us to sort sequences or strings of characters that come from some kind of finite alphabet. So an important question you might ask yourself is, well, is Radix sort better in practice? Like, I get that it's a cute and powerful idea mathematically and intuitively as a building block to solving problems, but is it better? Should I be using Radix sort or merge sort for practical tasks? So we're going to analyze this in 3 different ways. First, intuitively, next, using a more formal approach, and then finally, with an empirical approach, where we'll run some experiments. So we'll start with this intuitive approach, and I'll say this. So merge sort, okay, the first thing we need to do in order to make a comparison is address the fact that merge sort requires theta in log n compares, but if we want to make an apples to apples comparison between merge sorts and radix sorts, I want you to tell me, what is merge sort's runtime on strings of length w? Okay, so if I give you a string of length w, what is the runtime of merge sort if it takes in log n compares? It's actually a harder question than it might seem. Okay, so my answer is that it depends. It depends on the structure of the strings. So if the strings are very different, that is, they're all different in their top character, then each comparison would take constant time, and the overall runtime would be theta n log n. Now, if instead all of the strings are equal, or very, very close to equal, then each comparison is going to take theta w time. And so the overall runtime would be theta w n log n. So I just want to raise this point that an important question when trying to decide about the performance of merge sort versus, say, a radix sort, we need to take into account the fact that the structure of the string matters. That if the strings are highly different, the comparisons are cheap, and merge sort's a little faster. If the comparisons are costly, then merge sort will be relatively a little slower than it might be otherwise. So that's merge sort's runtime. It's actually not just n log n, it's between n log n and w n log n, depending on the structure of the strings. Okay, so let's start by just thinking about LSD sort, and it's the simplest of our radix sorts. Well, there's only 2, LSD and MSD radix sort. And so the facts here are that if we treat the alphabet size as a constant, so we just think of r as a constant, then LSD sort's runtime is theta wn, and merge sort is between n log n and wn log n. Now, if I want to know which is better, the short answer is it depends on the specific input. And so what I'd like you to do is think about, when do you think LSD sort might be faster, and when might merge sort be faster? So I would take answers from you, but you're not here. So come to lecture if you want to do the interactive version, and I'll just spoil it with my answers. So LSD sort might be faster if, well, for sufficiently large n, if we keep getting bigger and bigger and bigger numbers of strings, and we hold w constant, then eventually LSD sort will dominate. Now, if that's not the case, if the strings are simply just very similar to each other, in that case it seems plausible, just intuitively, that each every comparison in merge sort is going to cost w time. And so you can imagine that LSD sort would have a little bit of an edge, because it's going to look at every character exactly one time, whereas merge sort is going to reuse some characters. Now, if it's not clear that merge sort will reuse some characters, don't worry, we're going to go into that in more detail soon, but it seems plausible that if the strings are similar to each other, that LSD sort might maybe be faster. And when might merge sort be faster? Well, that can happen if the strings are really different from each other. In that case, each of our merge sort comparisons is going to be very fast, and so we can imagine that maybe it's faster. Okay, this is just an intuitive look, but we'll be doing a more rigorous approach in a moment. Okay, so that's the intuitive look. And so now let's try and formalize that a little by looking at a formal cost model approach. And I'll start that off in the next video.